In this lecture, we shall analyze the cantilever beam for the shear force and bending moment values over the length for a concentrated moment acting at the tip. Let's draw a cantilever beam with fixed end A and free end B. Let us show a clockwise concentrated moment M acting at the tip. We also show an arrow at point B towards the left and name it as X, indicating the distance of the imaginary section from this reference end. We now draw the projections from the points A and B. Upon investigation of the right part in equilibrium created by the imaginary section, we find that there is no load acting and hence the resistive shear force at the section also does not exist. The clockwise moment M acting at the tip causes a hogging resistive bending moment at the section, which remains the same for all the sections along the beam length. The bending moment equation hence can be written as minus M, which is a constant and independent of the variable x. The bending moment diagram hence is plotted with a uniform value of minus M along the entire length of the beam. It is also worthy to note a variation of the moment acting on the beam apart from the concentrated moment, which gives the same effect as the former. Sometimes a location on the beam, say the free end, is extended vertically as a frame by a distance y both upwards and downwards as a part of the beam, where a horizontal load P acts at the upper tip towards the right, while another horizontal load P acts at the lower tip towards the left. This creates a clockwise moment of value twice P times y at the free end B, which may be used for the calculations instead of moment M. Likewise, suppose we have a right angle frame of height A and width B as an extension to the beam, say at the free end B, over which we show a downward point load P at the end of the extension as indicated here. We try to have an equivalent load system acting at B without the extension frame for ease of analysis. For this, we show two loads of value P each in upward and downward direction at free end B along with the load P acting on the frame. We hence have a point load P acting at the free end B acting downwards as one of the loads, and the other load is in the form of a clockwise couple of value P times B also shown acting at the free end B. Further, we can increase the complexity of the applied load acting on the right angle frame extension by having an inclined downward load of value P given the amount of slope. We first denote the vertical and horizontal components of load acting separately on the frame extension using simple trigonometry. Let's call these as PV and PH respectively. The effect of PV on the frame is to produce a load PV acting downwards at free end B along with a clockwise couple of PV times B as discussed earlier, while the effect of horizontal load PH on the frame is to create a leftward directed load acting on the free end B of the cantilever along with a counterclockwise couple of value PH times A. These simplified representations of applied forces and applied moments can now be used for carrying out further analysis. In the next lecture, we shall consider solving a problem consisting of a cantilever beam with a combination of each of the loads discussed till now.